Hello everyone. We will wait for 2 minutes. So if anyone wants to join, so we'll wait for them. So let's start. Uh, Good evening, everyone. My name is Asma Parveen. I am a PhD student at IIT Kanpur. I am one of the TA for this course. So for what we'll do for today, we will go through a brief recap of what was taught in the previous week. Then we'll solve the assignment questions, followed by um, 5 more numericals based on the assignment questions. So shall we start? Okay, good evening, Mukesh ji.
Yes, madam, go ahead.
Okay. So is my screen visible?
Yes, madam.
Okay. So I will start from energy production from plastic waste. I am not covering the improvement of power plant efficiency. That was already in the previous week also, but 2 to 3 questions are in this week also. I request you all to go through that material. If you have any doubt, you can ask me. But today we'll start from plastics. So the course is taught by Professor P. Mandal from Chemical Engineering Department, IIT Kanpur. So there is one more participant. So we will start. So we have seen energy extraction from municipal solid waste. Now we'll see from how we extract energy from plastic. It accounts for around 10% in municipal solid waste of India. So these are the contents. So first, what is plastic? Basically, plastic is made up of polymers along with some additives and colors to improve its properties. So plastic, earlier, all the materials were made from natural products like from wood, from ivory of elephant. But after the invention of plastics, it replaced all these. But slowly, there is lot of plastic in our environment, in our ocean, and it is predicted by 2050, we will have more plastic in ocean than the fishes. So plastic waste is causing a lot of damage to our environment. One of the problem with plastic is that it is non-biodegradable. Its size reduces from to micro to nanoparticles, but its degradation is very slow. It takes hundreds and thousands of years to degrade plastic. So the plastics are typically organic polymers of high molecular mass, and along it contains some other substance like fillers, plasticizers, and colorants. So fillers are added to improve its performance or to reduce its cost, and colors is added to give different colors to the plastic. So as it is stated that some of the additive even can be toxic. So overall, many plastics are very toxic, like PVC, and burning of PVC is not allowed because it produces lots of acid and dioxins, which are not good for health of humans and other organisms. So there are two types of plastic: thermosetting plastic and thermoplastic. So by exposing thermoplastic to high temperature, there is no change in the composition of the material, so we can again and again reuse it. But what happens with thermosetting is that its properties changes with when we expose it to high temperature. So we cannot uh, uh, deform the thermoset set plastics and reuse. So here these are the types and code of the plastic along with some of the examples in which they are used. PET is used in beverage bottles, medicine jars, clothing, and carbon fiber. High density polythenes are used for containers for milk, shampoos, conditioners. PVC, that is polyvinyl chloride, it is used in all types of glass pipes and tiles. Low density polythene, it is used in sandwich bags, squeezable bottles, plastic, grocery bag. So uh, polypolythene, it is used in lunch. Polypropylene is used in lunch boxes, margarine containers, yogurt pots. Polystyrene is used in disposable coffee cups, plastic cutlery, etc. And these are the other categories which are used in nylon, polyactide, etc. So these are some of the plastics given. What is the formula of the monomer and what is the name of the monomer used? For example, if you take PVC, that is polyvinyl chloride. So the monomer is also vinyl chloride. Only poly is added because many numbers of chain of vinyl chloride are connected through bonds to form polyvinyl chloride. So these are some other types of plastics along with their monomers. So here is a table showing which suitability of different plastics for use for energy production. So polyethylene, polypropylene, and polystyrene are very good for production of energy. But we can see polyvinyl chloride, polyurethane are not suitable, and these should be avoided because on burning or in they produce very harmful gases. So they are not used for energy production. Also, PET should be avoided, and for fiber reinforced plastic, some pre-treatment are required to remove the fibers and then they are processed for energy production. So here is a graph which shows that the annual production of plastic was 245 million metric tons, which increased to 311 million metric tons from 2008 to in 2008 it was 245 million metric tons and it is increased to 311 million metric tons in 2014. So there is increase in the production and use of plastic. So there is very high need that we should control how to recycle and reuse the plastics. So this is a bar chart showing the composition of plastic in India. So around 9% of the MSW in India is composed of plastics and around 10,000 tons per day of plastic is generated per day in our country. So, as I said that there is a high need for proper management of plastics because we can see lots of plastic litter on the roads, on the near the dustbin. In fact, if the plastics are engineeredly deposited on the landfill, then also there is leaching of chemicals from the plastics and which becomes part of the leachate and it needs to be managed properly. So for plastics, since it is non-biodegradable, so the recycling and reuse of plastics is very, very important that we reuse and recycle all the plastics generated, then only the problem of plastic waste will be solved. So one of the technology to recycle the plastics is pyrolysis, in which the plastic is pyrolyzed to produce some liquid fuels. So some of the options for recycling is primary recycling, in which the characteristics of the product after recycling is similar to the original form. In secondary recycling, the final characteristic of the product is different from what was before recycling. And in tertiary recycling, we try to produce some amount of uh, fuel which can be used in different, which can be used for different purposes. And in quaternary recycling, what is done is plastic or other waste is burned or incinerated to get the energy, but this process is not in use in India. So what Central Pollution Control Board recommends is use of plastic polymers in for making roads, for you burning plastic in gasifying plastic in plasma gasification, and production of liquid fuel from plastic waste. So we'll see how to recycle waste plastic through pyrolysis. And what happens, waste plastic is fed in pyrolysis reactors, and as we know, in pyrolysis we get three end products. We will get liquid, we will get gas, and we will get solid. So the liquid fraction here will be LPG, it will be some sort of gasoline or fuel, waxes, higher olefins, and gas will have some of gas may be composed of CO, carbon monoxide, hydrogen, CO2. So gas will also contain some amount of energy. And the solid or char we will also get some part of solid or char. So generally, pyrolysis is done by thermally by applying temperature or by using catalyst. So polyethylene and polypropylene can be degraded thermally or catalytically to produce liquid and gaseous hydrocarbons. So there are a number of processes developed worldwide, but some of them are used to produce liquid products, a sort of plastic crude, and we will discuss what are the some of the technologies in the later slides. So here is a similar numerical we will discuss in the assignment problem. So we'll move forward. So here it is the reaction mechanism, that how plastic is formed. I request you to go through the slide to get the idea about this. Then the pyrolysis process. As I said, there is two processes. First is thermal pyrolysis and second is catalytic pyrolysis. So in thermal pyrolysis, high temperature is applied to convert the plastics, liquid plastic into some sort of fuel. And in catalytic pyrolysis, the temperature is reduced. Also, reaction time is reduced because of the use of the catalyst. The quality of fuel which we get as the end product, it is also improved, and it narrow down the product distribution of carbon number, that is cetane number is also improved. Here is a example, product yield at 425 degrees centigrade from real waste plastics in batch reactor. So here we can see that if we are using thermal pyrolysis, then we are getting 76.7% of oil. And if we are using catalytic pyrolysis with zeolite as the catalyst, then the oil yield has increased from 76 to 7% to 81.4%. And gas has also increased from 7.3% to 9.6%, but the solid content char has reduced from 16 to 9%. So our goal is also to improve the content of liquid, that is oil, after pyrolysis. So catalyst pyrolysis gives better fuel as compared to thermal pyrolysis. So what will be the end product, what will be its quality, all this depend upon what are the factors which affect the end product of pyrolysis, is what type of plastic we are feeding on the reactor, what temperature we are working, what is the residence time in the reactor, what are the catalyst we are using, what is its loading, what is the contact mode between the catalyst and the plastic waste which we have fed, and what is the type of the reactor. So some of the type of reactor which is used is batch mode. Like we fed the plastic, we gave the proper temperature, proper catalyst, we close the reactor, and once the pyrolysis is done, we get the end product. So to get again for batch mode, we will again fed some amount of plastic catalyst, and then let the process to complete, and then we will get the product. So this is the batch mode. We can also work in continuous flow mode, in which we will continuously feed the plastic and we will get the end product. So other type of reactor is fixed bed, and next is fluidized bed reactor. So in catalytic pyrolysis, two kinds of decomposition mechanism works. First is thermal cracking and next is catalytic cracking. So in thermal cracking, there is random scission in taking place in the polymer. Generally, the scission takes at the end of the chain and elimination of the end groups takes place. In catalytic cracking, what happens is uh, some beta scission and desorption takes place. You will get about what is beta scission in the mechanism of how plastic polymers are formed. So, what are the benefits we get from catalyst is that it increases process selectivity. So, decomposition with the use of catalyst, decomposition can take place at low temperature with lower energy consumption. Also, with use of catalyst, there is a reduced in the overall operation cost, and also the liquid product we get is better than what we get in thermal cracking. So the catalyst we use is generally heterogeneous catalyst, because the heterogeneous catalysts are more easy to recover after the process than homogeneous catalysts. So heterogeneous catalysts are the one which have different phase than the reactant. So if reactant is in liquid phase, then catalyst will be in solid or gas. Heterogeneous catalyst will be in solid or gas phase. And the homogeneous catalysts are the one whose phase is same as the reactant. So some of the heterogeneous catalysts which are used are zeolite, silica alumina, solid acids, etc. So the common steps for converting waste plastic to fuel is, first, there is collection of the MSW, and the plastic are segregated. So there is collection and segregation. After segregation, there is sorting of plastic waste based upon what is the type of the plastic. We segregate, we sort, like if we have polyethylene, we will sort all the polyethylene plastics at one place. Then we will sort the polypropylene, PVC plastics, etc. Next is shredding. In shredding, plastics are shredded into smaller parts on uniform smaller particles to be fed in the pyrolysis reactor. Next, the shredded plastic is fed into the hopper and then flow. And then after the feeding, the plastic is converted into some sort of liquid, which is again then fed into the pyrolysis reactor. After then, there is movement of liquid vapor into the condenser. After pyrolysis, uh, 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 that liquid plastic is converted to gas, some sort of vapor, and this vapor is condensed to get the fuel in the form of liquid. So finally, the liquid fuel is collected as the end product. So we'll move to next slide. So here is a process flow sheet for the pyrolysis. What happens here? The feedstock is applied, which is some pre-treatments is done, like there is cleaning, shorting, drying, and then size reduction. After all these pre-treatments, heat is applied to melt the plastic, and these melted feed are applied to the pyrolysis reactor. In pyrolysis reactor, due to presence of catalyst and heat, these plastics are get decomposed, and they produces three end products. First is the solid, which is the carbon char. We'll collect it separately. Then it produces vapors, which goes to the distillation chamber, from where we collect different fuels. These are the liquid fuels, and the end product, which is the pyrolysis gas. It has some calorific value, which after cleaning in the gas scrubber is sent back to the pyrolysis reactor for heating. So here we will discuss some of the reactors used for pyrolysis. So it is a batch reactor which works in the range of 300 to 800 degrees centigrade. Here plastic waste is fed, it is closed, and after the pyrolysis, gas is collected from one end. So advantage of batch reactor is that it is very easy to control the parameters, and also the design is very simple. But the disadvantages is that while working in different batches, it is possibility that the end product will have some variation in it. So while working in batch reactors, there is variability of products from batch to batch. So there is a difficulty in separation of catalyst. High labor cost per batch is required. There is difficulty of large scale operation. Also, there is more coke formation, and there is a lot of catalyst deactivation in batch mode reactors. Next is a fixed bed reactor, in which catalysts are supported on fixed bed. Here the plastic is fed from one end, then it gets in contact with the catalyst, and finally we get the end product. So the advantages of fixed bed reactor is that it is a continuous process and it is less labor intensive. So the labor cost will be lesser in fixed bed reactor. So, but the disadvantage with fixed bed reactor is that since the catalysts are placed on these supports, so some of the surface area of catalyst is not exposed to the reactant. So there is the available surface area of the catalyst may not be exposed to the reactant. So next is the fluidized bed reactor. As we know, in fluidized bed reactor, the high velocity gas is applied to make the reactants. Some sand is used for for fluidizing. So sand and everything in the reactor is in motion. So what happens here? The catalyst sits on a distributor plate, and the fluidizing gas carries in the and the reactant we feed in here is in the liquid state, and the temperature range here is in between 290 to 850 degrees centigrade. So fluidized bed reactor is more efficient than batch mode and fixed bed reactor. Some of the advantages is here that it can work in continuous process mode and it is less labor intensive. We get improved heat transfer. We get narrower and more uniform spectrum of products. The end product is more improved and uniform. So there is better mixing of catalyst and reactant because of the fluidization. And there is a very easy, we can scale up the lab reactor or pilot scale reactors to commercial level. But the disadvantage with it is that it requires lot of operations to be done to control the reactor. So next is a screw reactor. So it can also work in continuous mode. It has better mixing properties, but the disadvantage is that it has a low heat transfer with respect to fluidized bed reactor. So fluidized bed reactor is better than the screw reactor. Next is a conical spouted bed reactor, in which the waste is fed from the top and nitrogen gas is applied to carry the product out of the reactor. So we have good mixing with and it can handle large size particles with difference in their particle densities. So it is better in terms of fluidized bed reactors. It has better bed segregation than FBR. But the disadvantage is that it is a complicated instrument. So their design is very complicated and there's lots of challenges during operation, catalyst feeding and entrainment. So here are some of the companies which work to produce energy from plastic waste. So one such is Osmotech Pty Limited Australia. So they use different ratios of different plastics as feed, and they produce high grade diesel. Next is a company in USA which fed polyethylene and polypropylene, and they produced out around 0.78 kg of oil out of 1 kg of plastic. Next is a company in Japan which uses waste plastics, and they produce pyrolysis oil. So these are one is from India, Pyrocrate System, Mumbai, India, in which both plastics and tires are used as feed, and we produce pyrolysis oil, which can be used in industries as diesel. The capacity of this plant is 1. Was I audible? Because I got disconnected. Can anyone confirm? Am I audible now?
Ma'am.
Yes. So in Indian scenario, the waste plastic like polypolythene and polyethylene low density plastics, low polymer wax packs, these are fed to the pyrolysis reactor, and we get two end products. First is whatever the gas or vapor is produced, it is condensed and we get liquid hydrocarbons. And apart from this, the gases which are left, and these are these are treated to get the gaseous hydrocarbons. So three types of catalysts are used uh, for different end products to get. Catalyst type 1 is used for aromatic rich liquid hydrocarbons. Catalyst type 2 is used for gasoline rich liquid hydrocarbons, and type 3 is used for diesel rich liquid hydrocarbons. So there are three options: that there is waste plastic, we can produce gasoline from it, or we can produce petrochemicals, or or we can produce diesel out of this plastic waste. So you go through these numbers. So here is a comparison between the gasoline which is obtained from the waste plastic and what is the Indian standards for Indian petrol specification required to meet Euro 3 norms. So the color should be orange, and what the color which we get from the gasoline obtained from plastic waste is orange red. We can see that density is also in the range. So only there is little bit lesser recovery of carbon, but almost almost many properties can meets with the standard set by Indian petrol specifications. So these are some of the comparisons again. So again, here is one more case study from Siner Plastic to Fuel. Siner is a company. It commercialized pyrolysis and distillation technology to convert waste plastic into liquid hydrocarbon fuels. This It was a developing technology in 2004, and first full-scale plant was started in Ireland in 2008. So what this company says is that they produce a synthetic fuel that is clean, low in sulfur, and it has better cetane number than the general diesel fuel which is used. So the feedstock they use is the waste plastic such as packaging scrap, oil or detergent bottles recovered from households, and agricultural plastic waste. So the technology they use is that the feedstock is chipped or they are shredded to approx 0.15 mm, followed by then it is washed and dried. Then the feed is applied, sent to the pyrolysis chambers. There it is pyrolyzed at the temperature of 370 to 4 degrees centigrade, and the pyrolysis gas is condensed to get the liquid fuel and the gas. So these are some of the output results. So we'll move to next part, that is gas cleanup. So all the technologies, incineration, gasification, pyrolysis, or energy from plastic, they produces gas, and these gas contains lots of uh, uh, pollutants which may cause air pollution. So first we need to trap them, and then the clean air is then clean air is uh, sent in the atmosphere. So the main pollutants present in the flue gas is it may contain particulates or it may contain gas molecules. So for particulate removal, we have gravity settling, electrostatic precipitators, back filters, and cyclone separators. And for gas molecule removers, we have technologies absorption, adsorption, and there are some more technologies related to remove specific gas components like SO2, NOx, and CO2. Then we have weight scrubbers which can remove both particles and gas molecules simultaneously. So here is the typical gas composition which we get from different processes: incineration, gasification, pyrolysis of biomass and waste, and pyrolysis of waste plastic, and anaerobic digestion, which we'll discuss in the next module. So we can see that more or less we are getting CO2 in each gas we are getting SOx, NOx, and in waste plastics we are getting HCl and dioxins. CO is have some heating values, so it is used to get the heat, and eventually from CO2 is produced. So we have to remove CO2 from the gas. Then again, methane has calorific value, hydrogen have calorific value, so these are not to be removed. So next, we will first discuss the technologies to remove the particulates from the gas. So first is gravity settlers. What happens in gravity settlers is that because of the gravity force, the particles while moving in the chamber, they get deposited because the forces these particle experience is their is the weight of the particle in the downward direction. There will be some buoyancy force in the upward direction, and there will be drag force. So after some time, what happens that these that the resultant force becomes zero, and these particle moves with a constant velocity, which is not the settling velocity. So because of this velocity, these particles get deposited at the bottom of the settling chambers, and clean gas comes out. So, but the limitation with gravity settlers is that we can remove larger size particles, that at least particle size should be 50 micron. But the advantage of gas settlers is that it is very easy to operate. It does not require much operation than the other types of technology like cyclone separators and other. It is most simplest of all the technologies, and some pre-cleaning is required. So if the L is the length of the reactor and H is the height, so if there is a particle here, then and if it get travel and get deposited at the other end, so the time taken to travel the H height and L length will be same. So L is the length and V is the horizontal velocity. This is the time required to travel the length L, and it is equal to the time travel to height H, that is H height divided by the vertical velocity, that is the settling velocity. So we can derive this equation using here. We just have to do the force balance in the particle, like gravity will weight of the particle will act in the downward direction, buoyancy will act in the upward direction, and drag force will act in the upward direction. So Fg equals to Fb plus Fd. After putting all the value of gravity force, buoyancy force, and drag force, we will get the final expression as like this, that is Vt equals to 4g dp dia of the particle, rho p density of the particle, rho g, this is density of the media divided by 3 cd into rho g. So CD is the drag coefficient, which depends upon what is the flow. For Reynolds number, it is for laminar flow, it is different. For transitional flow, it is different, and for turbulent flow, it is different. So CD depends upon the Reynolds number, and based on the Reynolds number, we can find out what is the CD, and we can put the CD in this equation, and we will get the terminal settling velocity. So next is electrostatic precipitators. In this, very high energy is applied into the discharged electrodes, which produces electrons, and these electrons charge the particles in the gas, and these charged particles, because of the electrostatic attractions, these get collected into the collection electrodes. So the gas is applied from this end, it gets charged and particles get charged and collected, and the clean gas is taken out from the other end. So there are two types of ESP. It can be a parallel plate precipitator or a wire and pipe precipitator. So if we see that there will be two velocities acting in the particles. One will be the horizontal flow velocity, and other will be the VPM, that is the velocity which will attract the velocity with which the particles will get travel toward the collection electrodes. So there will be a resultant velocity acting in the particle which will be VR. So the efficiency of ESP is given as 1 minus exponential VPM. VPM is the drift velocity, this, into AC. AC is the area of the collector electrode, and Q is the volumetric flow rate. We can substitute Q into L. Q is the volumetric flow rate into length of the ESP upon V, horizontal velocity by V. V is the volume of the precipitator. We can substitute Q by this V into capital V into small v by L, and we will get this expression. Next is there is a equation to find the drift velocity. We can substitute VPM by this and we'll get a different expression. So here is a numerical. We will discuss numerical in the assignment problem. Next is fabric filters, in which fabrics like cotton, nylon, polyesters, asbestos are used, and the dirty air is passed through these fabric filters, and the particles get collected in the fibers, and we get the clean gas. So fabric filters are very efficient that we can get the efficiency as high as 99.9% and more. Here we can feed particles more than 0.1, 0.01 micron to 1 micron. There is also advantage that here the pressure drop is low, but the disadvantage is that since we are using fibers, so we cannot apply moist gases in moist gases for trapping because these will clog the pores in the fibers. Here the temperature in which we work is below the temperature of the flue gas which we are feeding should be below 285 degrees centigrades. The removal here we get it is nearly equal to the electrostatic precipitators. So here are some of the mechanism. Particles are separated by inertial collection, interception, Brownian movement, or electrostatic forces. So the bag houses, these fibers need to be cleaned periodically to remove the particles from it. So we can use mechanical shakers, or we can use reverse gas or pulse jet to remove the particles from the fibers. So these are the values for air to cloth ratio for different types of bag houses. Like if we are using cleaning by shaking, then this is the air to cloth ratio required, and so on. So next is cyclone separator. What happens is we apply the particle laden gas from one end, and in cyclone separators, vortex is formed and particles experience centrifugal force along with their weight, and they while moving in this vortex, the particles are removed from the gas, and particles are collected at the bottom in the dust hopper, and the particle free gas is taken out from the top of the reactor. So cyclone separators consist of a rectangular part at top, followed by a conical part at the bottom, where the dust is collected. So here is some cut. It is called cut diameter. The cut point of the cyclone, which is the size of the particle, which can be removed from the stream with 50% efficiency. So for separation of the particles, the radius of the particle should be more than 0.2 d naught, where d naught is the dia at the outlet of the cyclone. So here are some, I told you that the particles experience centrifugal force, then they experience drag force. These are the expressions to find the centrifugal force and drag force. And dP minimum, this is the dia of the particle. The minimum dia of particle which can be removed from cyclone separators. So D naught is the dia of the top outlet, rho g is the density, mu is the viscosity, and after putting all these, we can find out what is the minimum dia of the particle which can be removed from the cyclone separators. So here is a comparison between particulate matter removal with different equipments. So in gravity settlers, we can remove particles greater than 50 micrometers, and the removal efficiency is generally less than 50%. In electrostatic precipitators, we can remove particle size with greater than 1 micron, and here the removal efficiency is 98%. But here high initial cost is required for setting up the ESP, and it is very sensitive to variable dust loading. Next is fabric filters. In fabric filters, we can remove particles greater than 0.01 microns with removal efficiency of 99%. But the problem here is that filters are using fibers which are susceptible to chemical attack. Next is cyclone separator. In cyclone separator, we can remove particles greater than 5 micron with efficiency of more than 90%. The advantage of cyclone separator is it is inexpensive and less maintenance is required. So move to last module. So we have discussed the technologies to remove the particles from the gas. Now we'll see the technologies to remove gas as well as the technology to remove particles and gas in one go. So through wet scrubbers, we can remove the particles as well as the pollutant gases from the flue gas. So the basic principle here is that some contact is provided between the scrubbing liquid and the particles or gas present in the flue gas. So the scrubbing liquid used is generally water, but we can use some other liquids also. So the liquid droplet, these capture the particles, and if some gas is to be trapped, then there is exchange of gas from the flue gas to the scrubbing liquid. So the mechanism of collection here is inertial impaction, interception, diffusion. So there are 4 types of scrubbers. First is spray tower, centrifugal scrubber, packed bed and plate column, and last is Venturi scrubbers. So Venturi scrubbers are most efficient and they can remove particles less than 3 micron. So these are some of the advantages and disadvantages of wet scrubbers, spray scrubbers. So in spray scrubber, what happens? Water is applied from top, and these water are converted to very small particles, and the dry gas is applied from here, and there is contact between these water droplets and the gas particles, and these gas particles get trapped in these water droplets, and clean air is taken from the top. But the problem with scrubber is that we are converting the problem of air pollution to water pollution. So the water which is collected is the bottom. It is polluted, and we need to treat this water uh, before before disposing it to some land water or any other groundwater. So next is packed bed and plate column scrubber. In packed bed, there is some packed bed on in these. The liquid scrubbing liquid is applied and dirty gas is applied from the bottom. There is contact between the liquid droplets and particles in the gas, and these are removed, and again we get the wastewater at the bottom which needs to be treated. And in plate column, there are plates kept, and the contact between the particles and the water scrubbing liquid takes place near these plates, and the clean gas is collected from top and the dirty water is collected from the bottom. So here is Venturi scrubber. In Venturi scrubber, the velocity of the dirty particles is increased by reducing the here is the throat of the venturi, where the dia of the venturi is reduced to increase the velocity of the dirty gas particles, and then it is fed in the cyclone, and also the liquid droplets are fed in the cyclone, and due to difference in the velocity of the dirty gas and liquid droplets, there is contact between them, and finally the water droplets trap the particles and it drop at the bottom, and clean gases sent out from the top. So here some expression are given to find the efficiency of the scrubber. And here is a numerical. So the absorption technologies. So the chemical absorbents used for removing the pollutants are monoethanolamine, diethanolamine, methyl diethanolamine, Flexorb, and the physical absorbents use are Siloxol and Rectisol. So here are some of the adsorbents used. Like we can use silica gel, activated carbon, or activated alumina. So I think these were discussed in the previous slides. So for specific removal of certain gases, like for SO2 removal, there are two methods. First is dry method and second is wet scrubbing method. In dry method, the metal oxide are used to extract to convert SO2 to sulfur element, and the sulfur is extracted and used for other purposes. And for wet scrubbing method, there is contact between scrubbing liquid and gas, and SO2 is trapped in the liquid, and then it is uh, and then other treatment technologies are applied, and these are some of the technologies which are patented by different companies, and finally as sulfur is extracted. So next is for NOx control. So to control the amount of NOx in the flue gas, some of the tricks is that the residence time at peak temperature should be minimum, and also the peak temperature should be reduced, because NOx is produced at very high temperatures. So if you reduce the peak temperatures, then there is a possibility that the NOx amount of NOx can be produced, can be reduced. Also, we should one of the tricks is to minimize the oxygen content for reaction with nitrogen, because nitrogen reacts with oxygen to produce NOx. So some of the methods for NOx control is that by modifying some of the operating conditions also, we can control the NOx. NOx is that low excess air combustion. If we are providing less excess air, then there is chances that oxygen will not be available for nitrogen to react and NOx will not be produced. We can use two-stage combustion, and next is flue gas recirculation, is that the flue gas produced is recirculated, and then and next is injection of water in stream in which NOx is trapped. So the technologies used for control of NOx is we can use absorption methods, or we can use adsorption method also. Some adsorbents can be used, or we can also use catalyst to reduce the NOx to nitrogen. So here is some of the operating conditions for different catalyst. These are the reaction where NO is reduced to nitrogen. So for control of CO2 is one of the greenhouse gases which causes global warming or climate change. So CO2 is also trapped, and the air after cleaning is released in the atmosphere. So the methods used for trapping of CO2 is, one of the method is chilled ammonia system, in which CO2 is reacted with chilled ammonia and ammonium carbonate or bicarbonate is produced. And again, and through the reverse reaction, we can CO2 can be consumed and it can be trapped from the flue gas. So we can achieve efficiency of nearly 90% through chilled ammonia separation. So these are some of the advantages. Next, we'll move to assignment questions. Is my screen visible? Please, anyone confirm? Yes. Okay, we'll solve the previous year assignment questions. So I'll give you guys 2 minutes for each question. So the first question is, the plastic material used for manufacturing of beverage bottles, medicine jars, rope, clothing, and carpet fiber is mostly low density polythene, PET, high density HDPE, or PVC. So I'll give you guys 2 minutes to just try to answer in the chat box. I will see from there. So I got one answer. I request others also to please write your answer in the chat box. Two minutes is over, but I have got only one answer. So I request everyone to please participate and write the answers. So the correct answer is B, that PET is used for manufacturing of beverage bottles. We have seen that in the slides. So next question is, in the following process, the components A and B are, we have to identify what is A and what is B. A either condenser, B pump, A throttling valve, or B condenser, A pump, B condenser, A condenser, or B evaporator. So I'll give you 2 minutes. Just try to answer in the chat box, and I request everyone to please participate and try to answer. So I'm getting answer from only one person. So I'll wait for 2 minutes for you guys to write the answer in the chat box. So I got two answers. We have four participants, but I'm getting only one or two answer. So the correct answer is C, that B condenser, that after and then from there the steam is first condensed, and then it is sent to, and through pump it is resent in through the boiler. So next question is, energy loss due to convection and radiation from boiler surface in steam process can be given by. You have to find out what will be the formula to find out the energy loss due to convection and radiation. So I'll give you 1 minute. Just write your answer. Everyone, please write your answer in the chat box. Till now, I've got only one answer. So the correct answer is A. These are the questions directly from the slide. So next question is, which of the following separation technique can remove particle of size greater than 0.01 micron more efficiently? First is cyclone separator, B filters or fabric filters, C gravity settlers, or D ESP. So I'll give you 1 minute. Just take your time and write your answer in the chat box. So I'm only one person is participating. So I request everyone to write their answers in the chat box. And then we'll move forward. So only one person is participating. So I'll give you 1 more minute to please write your answer, then only we'll move forward. So Vijay asked where to get old question papers and answers. So here we are discussing the previous year questions only with the solution. So you can refer these the weekly discussion sessions held on Saturday and Sunday to get the previous year questions.
Okay, ma'am.
Okay. So we'll move forward. Only one person is participating and the rest are not writing their answers in the chat box. I'm requesting all to just write your answer in the chat box. No problem if it is wrong, if you have not seen the slides, but just try once to answer the questions. So the answer for this is fabric filters. As we have seen now that the fabric filters are more efficient and we can remove particles greater than 0.01 micron with very high efficiency of 99.9%. So next question is, which of the following chemical can be used for physical absorption for gas cleanup? Uh, First is Flexorb, then MDEA, Selexol, or diethanol ME. So you have to write your answer in the chat box. So I'll give you 2 minutes. Just take your time and write your answer in the chat box. So we have 5 participants, but I am getting only one answer. I request you all to please participate and write your answer. If you will not write, you will not participate, then we will not move forward from this question. So the correct answer is C. Selexol is used for physical absorption for gas cleanup. So next question is, which of the following statement is not true about catalytic pyrolysis? A, process operates at low temperature than thermal pyrolysis. B, it requires high residence time than thermal pyrolysis. C, the quality of liquid product is better. Or D, the product distribution of carbon number is in the range of gasoline and diesel. You have to find out which of the following statement is not correct. So I'll give you 2 minutes to write your answer. So I got one answer, and for the last question also I got only one answer. So I request everyone to just write your answer in the chat box. I'll give you 2 minutes. So the correct answer is B, is that it requires high residence time than thermal pyrolysis. In catalytic pyrolysis, the residence time is lesser than the thermal pyrolysis. So answer is B. So the name of the following pyrolysis reactor is, the reactor is in the top right corner of your screen. You have to find out which reactor is this, which pyrolysis reactor is this. So I'll give you 1 minute. Just find out what it is and write your answer in the chat box. So the correct answer is B, conical spouted bed reactor. So move to next question. 8, 9, and 10 are numericals. So I'll give you 3 minutes, 3 minutes to solve each numerical. So the first one is we have to find the yield. In a laboratory, a 55 gram of plastic waste is pyrolyzed in a batch reactor. Weight of the reactor is 750 gram. Weight of the collected oil is 37 gram, and final weight of reactor is 755 grams. The yield of gas, liquid, and solid fractions are, we have to find the yield of the gas, liquid, and solid. So I will give you 3 minutes to solve this and just write your answer, whatever option you are getting, and write it in the chat box. So we'll see how to solve it. So to find out the yield of that, how much percentage of liquid is produced, we will find out by how much weight of the liquid is produced, which is 37 gram of oil divided by weight of the feed. The feed given is 55 gram. So the percentage of liquid will be the amount of liquid oil produced 37 divided by amount of feed, that is 55 grams. So we are getting the percentage of liquid produced as 67.3%. Similarly, we will find out the solid percent as weight of the solid produced. So initially the weight of the reactor was 750 and final weight of the reactor is 755. So 5 grams of char has deposited in the reactor. So the weight of the solid is 755 minus 755 upon the weight of the feed, that is 55 into 100, that is 9.1%. And for the yield of the gas, we will subtract the liquid percent and solid percent from 100, and we will get the percentage of gas as 23.6%. So correct answer is B. So move forward. So question number 9 and 10th, these are common data question. The data from question 9 will be followed in question 10 also. So it is based on ESP. A municipal solid waste power plant is emitting 50,000 meter cube per hour flue gas. It is proposed to install an electrostatic precipitator with a collection efficiency of 96%. Calculate the total area of the collection electrodes. Drift velocity is given as 0.15 meter per second. So we have given efficiency, the flow rate is given, drift velocity is given. We have to find out how much area of the collection electrodes is required to get the removal efficiency of 96%. So I'll give you 3 minutes, just solve this question and write your answer option, whatever you are getting in the chat box. So I got two answers. Soham is telling it is C and Vijay is telling it is D. So let's see what is the answer, correct answer. So C is the correct answer, 298 meters square. So first we will convert the flow rate from meter cube per hour to meter cube per second. So 5,000, 50,000 divided by 3,600 will give us 13.88 meter cube per second. So for ESP, we know that efficiency is given as 1 minus exponential to the power of minus BPM drift velocity into AC area of the collection electrodes divided by flow rate. So we just have to put the efficiency as 0.96%, 0.96, drift velocity as 0.15, Q as 13.88. We have to solve this. Since it is e to the power something, we will take a natural log ln both sides and we'll find out the area of the collection electrode as 298 meters square. So correct answer is C. So next question is also based on the question number 9, that in question 9, what would be the additional collection electrode area would be needed if the collection efficiency is 99.6%. So the collection efficiency has been increased from 96 to 99.6%. So we have to find out what will be the additional area of collection electrode required. So I'll give you 3 minutes for this question also. Just solve and write your answer. So I got one answer as C. Let's see. So the correct answer is C. We have to solve like previous one also only. Like we have given the Q as 550,000 meter cube per hour, and we know efficiency is 1 minus exponential to the power of minus BPM AC by Q. Here BPM will be same 0.15 meter per second. We have to find the collection electrode area. Q is given, so putting the efficiency as 0.996, that is 99.6% as 0.996, and then solving this equation, taking the log to find the value of AC, we are getting the area of collection electrode as 511.24 meters square. So for 96% removal, the area required was 298. And for 99.6%, it is 511.24. So the additional area requirement will be 511.24 minus 298, that is 213.24 meters square. So these were the questions for assignment 5 of previous year. Next, we will solve 3 or 4 more questions based on these concepts only. So here the question is, a municipal solid waste power plant is emitting 85,000 meter cube per hour of new gas. It is proposed to install an ESP with area of collection electrode as 500 meters square. Calculate the collection efficiency of ESP. Drip velocity is 0.109 meter per second. So we have to find what is the collection efficiency of ESP. We will use the same formula. I'll give you 3 minutes to just find your answer and write whatever value you are getting in the chat box. So we'll see how to solve this. Okay, I got one answer as 90.05%. Let's see. The flow rate is 85,000, sorry. It will be one more zero. Divide by 3600, that will be 23.611 meter cube per second. The collection electrode area is given as 500 meters square. Drip velocity is 0.109. We know what is Q is 23.611. We'll put these values in this expression and we'll get the efficiency is 0.9056, that is 90.56. So we'll move forward. There may be chance that I have done some calculation mistakes, so you just check once more by your own. So next is also based on ESP, is that suppose an ESP has a measured efficiency of 90%. We wish to upgrade it to 99%. By how much we must increase the collection area? So currently the removal efficiency is 90% and we have to upgrade it to 99%. So we have to find out how many times we have to increase the area of the collection electrode. So I'll give you similarly 3 minutes for this question. Just solve and write your value in the chat box. So we'll see. We know efficiency is given as 1 minus exponential to the power of minus Vp and AC by Q. We will find out for 90% removal. We will take this term as P. So exp minus P equal to 1 minus 0.9, 0.1. We'll take log on both sides. And this will be equation 1. For 99% removal efficiency, we will solve similarly. And this will be equation 2. So we will divide equation 1 by 2. And we will get the ratio of collection efficiency area required for 99% removal to area required for 90% removal as 2. So hence we have to double the area of collection electrode to require the removal of 99% from 90%. So next question is, is that dust has particles with migration velocity of 0.25 meter per second. So migration velocity and drift velocity are same. So the drift velocity is 0.25 meter per second for a total air flow of 234,000 meter cube per hour. What must be the number of collecting plates, each having area of 50 meters square? Assume collection efficiency of ESP to be 95% and assume collection on both sides of the plate. So we have to find out the number of plates required. So first we'll find out based on the removal efficiency, flow rate and drift velocity, what is the area required. Then we will divide it by area of each plate. Since it is given that the collection is on both sides of the plate, so area of each plate will be twice of this. We will divide it by total, we will divide the total area required by area of each plate and we will find out how many number of plates are required. So I'll give you guys 3 minutes. Just solve and write your answer in the chat box. So 16 plates is the correct answer. So I'll see how to solve this. So we have given the flow rate as 2,34,000. I will convert it from meter cube per hour to meter cube per second and we will get 65 meter cube per second. Then we know the formula for efficiency. We have drift velocity. We have given the area of collection electrode. We know what is Q. Sorry, we have to find out the total area for this removal. So we will find out AC, which is coming out to be 778.96 meters square. So the area of each collection electrode is 50 meters square. And since collection is on both sides, we will multiply by 2. So the number of collecting plates is 7.79, nearly 8, not 16. Because one statement is given that collection is on both sides of the plate. So since collection is both sides, so effective area for collecting for each plate will be 50 plus 50, that will be 100 meters square. So number of collecting plates required will be 7.79, that is nearly 8. So there is one more question. So again, it is based on electrostatic precipitator. Is that an electrostatic precipitator having plate each of length 5 meter, width 3 meter, with air flow rate of 2000 meter cube per minute, and the average particle diameter of 1 micrometer, and drip velocity of particles as 0.00547 meter per second. Calculate the number of plates required to achieve an efficiency of 99%. Assume collection on both sides of the plate. So this question is also sure. So this is the previous slide. Vijay, do you have any doubt? Okay. Shall we move forward? So this is the question. It is also a little bit similar to previous one. In this, the only difference is that we have to find out the area of each plate through length and width. So I'll give you 3 minutes. Just solve the question and write your answer, whatever you are getting, in the chat box. Then we will see what is the solution for this question. So we will see what is the solution. So flow rate is okay. So we'll check what is the answer. So flow rate is given as 2000 meter cube per minute. So we'll convert it to meter cube per second. The velocity is given and area of each plate will be 5 into 3. And since the one statement is given is that assume collection on both sides of the plates. So the effective area will be 2 times of each plate, each side of the plate. That will be 2 into 5 into 3, 30 meters square. Then we know that the formula for efficiency, we will put for 99% efficiency is given. We will find out how much total area of collection electrode is required. So the total area is coming out to be 28062.91 meters square. Okay. But Vijay, the flow rate is given in meter cube per minute. So we have to first convert it into meter cube per second because the Q here in the formula should be in meter cube per second. So we will get the total collection electrode area as 28062.91. We will divide it by area of each electrode plate, that will be 935.43, that is 936. So you are correct, the answer is 935. Since it is more than 935, so we'll take it as 936 plates. So there is one more question. It is based on Venturi scrub. A Venturi scrubber is being designed to remove particulates from a gas stream. The maximum flow rate is 30,000 cubic feet per minute, and the coefficient K for this system is 0.15. The proposed water flow rate is 180 gallons per minute, and the value of psi, that is impaction factor, is also given as 24.56, and the average gas velocity is 250 feet per second. So we have to find out, sorry, I have not given the statement. So we have to find out what will be the collection efficiency from this scrubber. So I'll give you the formula to find out. So the formula to find out the collection efficiency is in Venturi scrubber is E equals to 1 minus exponential K. K is given. L is the liquid flow rate per So there is some fluctuation in internet connection from my end. That's why I'm getting disconnected. So I'll reshare my screen. So what I was telling is that L is the liquid flow rate per unit per 1000 cubic feet per minute of gas flow rate. So L is the liquid to gas flow rate ratio. And psi is the impaction factor, which is already given in the question. We just have to put the values and we have to find out what is the collection efficiency. So I'll give you 3 minutes and just put the values and find out what collection efficiency you are getting. So I think the time is over now. So we will see how to approach this question. So K is the empirical factor which is already given. L is the liquid flow rate per unit gas flow rate. Sorry, liquid to gas flow rate ratio. Psi is the impaction factor which is also given. So we'll find out liquid to gas flow rate as we have to find out in gallons per minute per cubic foot per 1000 cubic feet per minute. So we have given 180 gallons per minute of the water flow rate, that is the liquid flow rate, 180 gallons per minute, and 30,000 cubic feet per minute is the gas flow rate. So liquid to gas flow rate will be, we have to take it as per 1000, so it will be 6 gallons per minute of liquid flow rate per 1000 cubic feet per minute of gas flow. So what we have to do is K is given, we have find out what will be L, and psi is given, psi. So we will put these values in the formula 1 minus E exponential minus K, that is minus 0.15 into L. L is coming out to be 6 into psi, that is 24.56 to the power of 0.5. We will solve this and we will get the removal efficiency as 98.84%. So is the solution clear? You guys have any doubt? Vijay and Soham, if you have any doubt in this question, you can ask me, or we shall, so time is over. If you have no doubt, then you can leave the meeting. Can any one of you can just confirm if you have any doubt or not? So I think you have no doubt. So thank you so much for joining. So I got one answer. Thank you, ma'am. Okay. Okay, thank you so much for joining. We will meet next week on the same day, on Sunday on same time, from 7 p.m. to 9 p.m. Thank you so much.